In this video I'm going to talk about some of the properties of logarithms. And I'm always going to use a base e, but any of these properties will work with any base. So I'm always going to be using the natural log when possible, but you can always replace this with log of any base. So the first property is that the log of xy is equal to the log of x plus the log of y. Alright, so what I'm going to do for each of these properties is just a short proof. It may be rigorous, it may not always be super rigorous, but it's the type of thing I'd like you to be able to do on your own later once you have some more practice with how logarithms work. So in order to do this proof, let's start by just reading off what the left side means. Well, the left side is really the power I raise e2 in order to get xy. And the right side of this equation is the power I raise e2 in order to get x plus the power I raise e2 in order to get y. Alright, so what we're going to do next is a very useful technique, and it's one that I think you'll see comes up over and over again. So what we do is we actually take this power and then we'll raise e to that power. So we raise e to the natural log of xy. What does this evaluate to? Well, we're raising e to the power that will give me xy. So e to the natural log of xy is just xy. But on the other hand, if I raise e to the natural log of x plus natural log of y, well, recall one of our power rules says that if you have a sum in the exponent, you can write it as the product of the base to the first term times the base to the second term. So e to the natural log of x plus natural log of y is equal to e to the natural log of x times e to the natural log of y. But e to the natural log of x is just x, and e to the natural log of y is just y. So what you get is x times y. Are we done? Almost. What we've shown is that e raised to natural log of x times y is equal to e raised to natural log of x plus natural log of y. But we have to show that these powers are the same. And here we'll use a really useful result. Because e to the x is an invertible function, it is a function with an inverse. Because e is an invertible function, if e raised to some power is equal to e raised to another power, then those powers must be equal. If e to the a equals e to the b, then a must equal b. So, since e to the natural log of xy equals e to the natural log of x plus natural log of y, we must have that natural log of xy must be equal to the natural log of x plus natural log of y. Now this doesn't just work for e to the x. Any invertible function has this really useful property that if the functions are equal, then the inputs must be equal. We'll use it again in these proofs, but really, anytime you see an invertible function, you can use this structure to your advantage. Okay, so we've proven our first property. Let's look at the second property that we're going to prove. So the second property says that the natural log of x to the a, and here we're taking the natural log of this quantity, that is equal to a times the natural log of x. We're going to use the exact same procedure as for the previous proof. What does this first term mean? Well, that's the power I raise e2 in order to get x to the a. So let's just do that. Let's take e and raise it to the natural log of x to the a. That needs to be just plain old x to the a. Let's look at the right side. If I take e and I raise it to a times natural log of x. Now I'm going to use another rule of exponents. That rule says if my exponent is the product, then I can write it as e to one of those terms and then raise the whole thing to the a. Alright, but now this term inside the parentheses, e to the natural log of x, is just x. So now I have x to the a. And so we see that e to the natural log of x to the a gives me the same thing as e to the a times natural log of x. So of course, because e, the exponential function, is invertible, this means that the natural log of x to the a must equal a times the natural log of x. And there we go. Okay, moving right along. Let's use those two properties I just proved to prove this following property, that the natural log of x divided by y is equal to the natural log of x minus the natural log of y. Now there are actually a couple ways to prove this, and in fact the ability to approach a question from many angles or to use different techniques is very valuable. It helps you build flexibility in mathematical problem solving, but in problem solving in general. So I would always encourage you to try to solve a question in multiple different ways. This way, the way we're going to do this one is going to rely on the previous two properties. So the first thing I want you to note is that natural log of x divided by y is the same as natural log of x times y to the minus 1. That's because x divided by y is the same as x times 1 over y, which is the same as x times y to the minus 1. So now we can use our first property, because the log of a product is the sum of the logs. Right? That's the first property that we proved at the beginning of this video. And now the natural log of x won't change, but now I can use the second property on my second term here, because the natural log of y raised to an exponent is the same thing as that exponent times the natural log of y. And our last step is just to recognize plus negative 1 times natural log of y is the exact same thing as just subtracting the natural log of y. And there we've just proven this property. Okay, there's one more property I want to prove in this video. So if I have two different bases, let's say I have the bases a and b, then the nice result is that the log base a of x is equal to the log base b of x divided by the log base b of a. Now when you look at this property, when you use it, the first thing you have to do is make sure that you're keeping track of your bases. The left side has a base of a, while both the logs on the right side have a base of b. Now, to prove this statement, I'm actually going to make a small change. I'm going to use, instead of the letter b, I'm going to use the natural log, because that makes it a little easier for me to write, and I think also in the end a little easier to keep track of. So what I'm going to prove is that the log base a of x is equal to the natural log of x divided by the natural log of a. To prove this, just like before, I'm going to take a and raise it to the log base a of x, and I'm going to determine if that is in fact equal to a raised to the natural log of x divided by the natural log of a. Because if this lower expression is true, it will force the two powers to be equal, which is exactly what I want. Let's consider this left side first. A to the log base a of x, hopefully you recognize what this is. This is just equal to x. So really the whole goal of the rest of this proof is simply to prove that a to the natural log of x divided by the natural log of a is equal to x. So we're going to be proving the statement here in the pink box. Now to do that, I have to do a little bit of setup. Alright, so let me do a little bit of setup. Let me take e, and I'm going to raise it to the natural log of a. And let me put the equal sign over here. So e to the natural log of a, hopefully you recognize that this is just equal to a. Now what I can do is I can take this whole thing on the left side and raise it to the 1 over natural log of a. Well, if I do that, I have to raise also the right side to the 1 over natural log of a. Now if we look carefully at this left side here, we realize I can use the properties of exponents to cancel the natural log of a with the 1 over natural log of a. And if that's not immediately clear to you, that's something you should review. So what does the left side simplify to? Well, the left side just simplifies to e. And the right side, of course, is a to the 1 over natural log of a. Now the last thing I'm going to do here is I'm going to raise both sides to the natural log of x. And then just do a little bit of simplification. So my simplification is simply to say that e to the natural log of x is equal to a to the natural log of x over the natural log of a. And this right here is the key result. And now let's look at why. Let's take this result and plug it in right up there. A to the natural log of x divided by the natural log of a, let me erase this, is exactly equal to, because of what my work has led me to, it is exactly equal to e to the natural log of x. But what is e to the natural log of x? Oh, that's x. And we've proved our desired result. And we wanted to prove that log base a of x is equal to the natural log of x divided by the natural log of a. And to do that, we proved that raising a to the left side is equal to raising a to the right side through this process right here. Okay, that was our last property that I've proven. I'm going to leave you with two properties that I want you to prove, and both of these are properties you can prove using nothing more than the reasoning and maybe some of the previous properties that I've proved in this video. So what I'd like you to try to prove is that the log base a of 1 is 0 for any base a, and that the log base a of a is equal to 1 for any base a. And if you want, you can do these with specifically the natural log, because if it works for natural log, it will work for any other base. But these two properties I think you can prove using either the previous properties I've proven or some of the techniques. So what were the techniques? Well, the techniques I liked the most were exponentiating both sides. Right? Because if we exponentiate both sides and we get equality, that will mean that the powers on either side must be equal. So that's a very good technique to use, especially for the properties we've proven here. And the other technique I used was I wrote out what log base a of x really means. And sometimes just writing this out and saying what this really means will lead you directly to the answer you're looking for. So these are two techniques that are useful here, and these are actually techniques that will be useful always as you do mathematics. The first technique relies on the invertibility. And that's a property of function that's really useful that I recommend whenever you have an invertible function, you rely on that property of invertibility. And the second technique is even more valuable. The second technique is just to reason your way through the question, to say what everything means, and to really understand what these mathematical expressions are trying to communicate to you.